We can also develop a crystal field theory diagram for a tetrahedral geometry. But in order to do this, we kind of need to think about how the molecule is oriented along the axes. So I have a picture on this slide of how we can think about how the tetrahedron should be oriented compared to the Cartesian axes. So if we do that, we know that the d orbitals in the atom, they split into two groups in the tetrahedral point group, the T2 group and the E group. So the E group, the T2 group are pointed, but those are the XY, XZ, and YZ. They're pointed between the Cartesian axes. So if you look at this figure, you see that actually the ligands, the tetrahedral ligands, are pointed between the Cartesian axes at the edges of the cube, or the corners of the cube. So that will make the T2 ligands, so this is XY, XZ, and YZ, the T2 group, it is going to be slightly higher in energy, while the E ligands, these are x squared minus y squared and z squared, they are, because the ligands are oriented in the corners of the cube, the x squared minus y squared and z squared are actually between the ligand atoms, so they go down slightly. Like in the octahedral case, we see a difference that here we're going to call delta T, T for tetrahedral. Now, fun fact, it turns out that there is a theoretical relationship between delta T and delta O, and they're related by 4/9. This is derived in your book if you really care to find it, but it's really okay for us just to posit this. And so the point is that in general, the tetrahedral splitting is much smaller, about half of what we would see in a similar octahedral setting. So why is that? We get less splitting in the octahedral case because there are fewer ligands. So more ligands, you can think about like each ligand is contributing to the bonding. When there's only 4 ligands, we only get 4 ligands worth of contribution. So that's how we have this smaller difference. That's going to have consequences for things like the electronic structure. Tetrahedral complexes are almost always high spin. And I say almost always, so that because I'm just sort of leaving the option that maybe you could find a low spin tetrahedral complex. But when I say almost always, I really mean always, or as close to always as a scientist is willing to get. So delta T for a tetrahedral complex is really pretty small. That's also going to make these quite brightly colored because we have this low energy gap between the orbitals.